In this project, we will simulate two-phase flow inside an ejector. The geometry of this model is designed in Gambit software. The geometry of this model is also meshed in Gambit software, and the mesh type used for this geometry is structured.
By clicking on the subscribe button, you will be informed about the newest CFD training videos by Mr. CFD. Or if you are watching the training video, click on the Mr. CFD logo and subscribe.
A new window will appear showing you the domain extents of your geometry. Also, under the view length unit section, you can see the default geometry units, which is meter in this project. Also, under the scaling section, under the mesh was created in, you can change the settings in order to activate the scaling factors beneath that. For example, your geometry and mesh was designed in a software which its default unit was millimeters. By activating these scaling factors, you can change this factor to your desired factors in order to set the length to the appropriate unit. After double-clicking on the multi-phase button, under the Models tab in the appeared window, you can see that we have enabled the volume of fluid model, and under the number of Eulerian phases, as was previously mentioned, we have defined two phases. Click on the Thermal tab, you can see that the coupled thermal condition is defined for this boundary, which means that this wall is in contact with the fluid on its both sides. After double-clicking on the Initialization button, a new window will appear. In the appeared window, you will see that Hybrid Initialization method has been chosen, which means that an average is taken from different part of the computational domain, and these averages are set to be the first and initializing values for our simulation. Now in this contour, you can see the velocity distribution inside our computational domain. In the middle part of our computational domain, you can see the liquid ammonia passing with high velocity due to its high pressure in the inlet section. And along with it, the vapor ammonia will entrain and exit the computational domain with the liquid ammonia. Now in order to extract the contours of volume fraction, all we have to do is to select phases under the contours of section, and underneath it select volume fraction and your desired phase. After defining those parameters, by clicking on Save or Display button, the software will show you the volume fraction contour. Now in this contour, you can easily see the changes of volume fraction of the liquid, and you can easily see the interfaces separating two phases of liquid and vapor ammonia. Now in this slide, you can see the streamlines of two phases of liquid and vapor ammonia, and you can see the flow patterns caused by the high velocity liquid ammonia passing in the middle section of our computational domain. Finally, a summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product.
In general, an ejector is a system of ducting and nozzles used to direct the flow of high-pressure fluid in such way that the lower pressure fluid is entrained in the jet and carried through a duct to the region of high pressure. It is a fluid dynamic pump with no moving parts, excepting a valve to control the inlet flow. A steam injector is a typical application of the principle used to deliver cold water to a boiler against its pressure, using its own live or exhaust system, replacing any mechanical pump. In this project, two-phase flow of vapor and liquid ammonia in a two-phase ejector has been simulated by ANSYS Fluent software. The realizable k-epsilon model is used for flow analysis. The VOF multiphase model for two phases of liquid and vapor ammonia has been used to investigate the phase interaction. The energy equation is also activated in this analysis. The liquid ammonia will enter the computational domain through the primary inlet with the pressure of 9 megapascals and a temperature of 393 Kelvin. This flow will induce the vapor ammonia to exit the ejector along with liquid ammonia. The geometry of this model is designed in Gambit software. The geometry of this model is also meshed in Gambit software, and the mesh type used for this geometry is structured. The element number is equal to 11,808. To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.